in the second part of the compression unit, I'd like to look at repetitive texts in a different sense. The first part was about characters of different frequencies, and then we saw how Huffman can exploit that. Now we'll try to look at repetitions on a bigger scale. I want to motivate this a bit with this maybe well-known example. I don't know. I don't know if this qualifies as a natural text, but more sensible natural text also has the feature that there appear the same words many, many times. Words like the and well, you know, the frequent words in English and in other languages, they just occur many times. But that doesn't necessarily mean that the character frequencies reflect that in exactly the same way. And in this extreme example, I think this becomes quite clear. Suppose this text keeps going over pages and pages, and it's always the same sentence repeated again and again. So if you compute the entropy, which we've seen is a good predictor of how well Huffman will compress this, you will see that the entropy of this text is not so low. In particular, you will have some contribution for each character, and that contribution is the same for every character, no matter how long the text is. That's how entropy works, after all. It goes character by character. And it doesn't in any way recognize that after a certain length, the whole thing just keeps repeating. So if we want to capture that kind of redundancy, anything that's based on Huffman or individual characters just won't work. You have to put in context, several characters at once to get this compressed reasonably. So it seems like the whole notion of compressing one character and replacing it with some code word is not strong enough. Instead, we have to use what's called phrases. So that's just substrings of the text, and replace a whole phrase by some code word. In this case, we would want a phrase that is just this sentence, and then there's some way of saying, just use this code word all the time, and hopefully the code word is much smaller than the sentence. Or maybe there's even a smart way of saying, let's use this code word now so many hundred times. Okay? And we'll see some examples of both of these ways of compressing. Now the challenge, of course, is most texts don't look exactly like that. They have some sort of repetition, but it's not as obvious as this and not as extreme as in this one. The first example of a code that can achieve something like this is a very simple one that's called run length encoding. And that's the simplest form of repetition one could think of. It's runs of the same character. So it's just the same character repeated several times in a row. And it might make sense to have to expect something like this if you think about black-white images that come from a scanner. Maybe it's scanning some page with a high resolution. You want to see all the characters nice in detail. But if you restrict it to 2 colors, we will see many runs of zeros and ones like in this example. For this section, we'll restrict the source alphabet to binary, which is not necessary to do in run length encoding. It just makes the algorithms a little cleaner. I'll comment on this at the end again of this section. It's not a very substantial restriction. The method can generalize. The idea of run length encoding is to use as phrases the runs of this character. So in this case, we have 5 zeros, 3 ones, and 4 zeros. That's slightly more succinct than saying 0, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, right? Now, if we want to store this, you can, of course, not simply list the numbers. You have to somehow convert that to binary again. And so we need a smart way to do that. But what run length encoding consists of is a little bit more structured. We have to tell the decoder what is the first bit. Do we start with a 0 or with a 1 in the entire string? And then we have to tell it how long each run is. We don't have to store anything else because you always know if I start with 0 and then there's a run of 17 zeros, the next run will be 1s. Otherwise, it would be the same run. So in our example, we store a 0 for, we start with a 0, and then 534 for the length of those runs. Okay? Easy so far? The question that comes up is, we have these numbers that we want to store. These are some integers. And well, at least in principle, these can grow without any bound. It could be that we get an input where there's a run of zeros of arbitrary length. Could be the entire file. So we have to be prepared to store an integer that we don't know how big it is. It could be as big as, well, we don't know. We don't know up front. So we have to be prepared to store an integer of arbitrary size. How do we do that? How do we do that in binary? And as a start, think about how programming languages do this. That's where the question gets at. Programming languages have to solve a similar problem all the time. They store strings, and the strings have variable length. But computer memory is just long sequence of bytes. There's no specific boundaries. How does a programming language handle this problem? How can it store strings of variable length? Try to be concise. So think about low level. If all your computer has is this, think about a word RAM. Okay, you have one big array and each cell can contain a number. How can you store a string so that a user program can know this is hello world and then it stops without knowing how long the string is in advance? It could be as long as the user gives you an input. Okay, I'll show you some of the suggestions. Okay, this is, you just see the most frequent one. Yeah, I know you will start this game again, of course. No, it always jumps back. I can't scroll fast enough. I think the two main solutions that I know of have been in the list. Shockingly, they're not emoji. Okay, I'll keep you let you keep playing. But so the two solutions I know of. Option one, you prefix the string with the length of the string. So the first entry says now comes a string with 500 characters. So you know the next 500 cells contain characters that belong to this string. Now, there's a slight caveat here. You need to somehow restrict the strings to a length that fits in one word now, right? You have to fit that number in one word. So it's kind of cheating, but it works fine in practice because we don't need strings that are absurdly long. If a word on a computer now is 64-bit, 2 to the 64 is a really long, it's a really big number. Your computers don't usually have 2 to the 64 bytes of memory, not even close to that. And so it's fine. It's a little unsatisfactory in theory, maybe. The other solution is you reserve from the alphabet a special character and say this is the end of the string. And well, C traditionally uses null terminal, so the character that just consists of all zeros. The null character is the marker for the end of the string. It's part of the ASCII alphabet, but it's not allowed to be used inside the string if you use that convention, which is a restriction. So you need to make sure that the programs obey that, or you enforce it by adding another bit or something like this. Okay, these are the two options. Now what can we do for our integers of arbitrary size? It seems both are, at least from a theoretical perspective, not completely satisfactory. And also we want to do it in binary. Okay. There's a really nice way that is called Elias coding. What we need, just rephrase that a bit in different terminology. We want a prefix-free encoding for integers. Why prefix-free? Because we want to decode it, and that has helped us in the past, so let's stick with that property. But we want it to allow arbitrarily large integers. There should be no baked-in bound like in this store the length of the string first version. And we need to know when we're done. That comes with the prefix freeness, but this essentially means we cannot simply write down the binary representation of the number, because then we wouldn't know when one number stops and the next begins. What you probably didn't think about, but is completely obvious in hindsight maybe, is there is a simple encoding that satisfies both of these properties fine. That's the unary encoding. That's if you make ticks on the board to count something. I can represent a number by that many zeros followed by a 1 to signal the end. If I have two symbols and I only use one to represent the numbers, I have another one free for the end of word symbol. It's just that we don't like this encoding because it gets really long for even moderate numbers. So that's not great, but it exists, right? It's fine. Now it's much too long. And in a sense, the output has long runs, and we want to use this for compressing runs. So that seems to get us nowhere. Now the trick in Elias codes is the unary encoding of the number itself is crappy long. But what if we take the binary representation of a number, which didn't work by itself because we don't know how long it is? But we know to store a number in unary. So we store the length of the binary representation in unary using exactly that idea, and then append the actual representation. That doubles the number of bits that we need compared to just the binary representation, but it makes it prefix-free. And that's called Elias gamma code. Okay, I lied a little bit. Elias gamma code is a very slight refinement of that idea, because immediately if you do that, you notice two things. The length of the binary representation is always at least 1. We only represent natural numbers starting with 1. So we might as well store the length minus 1 instead of the length. Saves a bit. And the second observation is the binary representation of the number always starts with a 1 because we don't want leading zeros. And so we don't need the terminating 1 of this run length encoding either, just because there is always a 1 coming with what we append next. So, but with these two slide modifications, this idea is what's behind Elias gamma codes. So here are some examples. 1 is just mapped to 1. Now, how's that? 1 in binary is a single 1. The length of that is 1. We store not the length, but length minus 1. So we store 0 zeros followed by the binary representation, which is just 1. 0 zeros, 1 1. Okay? How does 3 work? 3 in binary is 1 1. The length of that is 2. Take off 1 means I have to put 1 0 in front of it. So 0, 1 1. Let's do 5 as well. 101 is 5 in binary. And so I prepend 2 zeros, 1 less than I have digits. And for 30, well, you can hopefully figure out that 11110 is 30 in binary. Yeah, 31 is 5 ones, so that looks good. And so we prepend 4 zeros because we have 5 digits in the binary representation. Okay? Apart from the brutal task of computing the binary representation of numbers, this is not too hard to do. Let's see if you get this one. Let's do the opposite. We decode. And to make it not so boring, I added more bits. So what you see here is a string that contains a number and other garbage after it. And you're just supposed to decode the first number that's encoded with this Elias code. Okay? I think you have the string in the question, so let me maybe go back to the slide with the instructions. And please send me the number in decimal, not in, you know, whatever that is. They're emoji for digits, right? How did you make one answer appear in colored? Is this also in that view? Okay, I haven't shown the... okay, a few more minutes. Okay, I'm not sure what the color code means. I'll show some answers because I want to get through some more exciting stuff too. I think the colors are just how often it was answered. Various things. Let's just go through this so that we do it once together. How do you start? First, you check how many zeros do we have. 3 zeros. That means the number I'm reading has 4 digits. So I have to take these 4. Sorry. So that's the number I have to decode. So what is... Okay, you don't see it. All right, sorry for that. The first 3 zeros tell you need to read 4 bits. These are the 4 bits. Now, what's that number in decimal? 4 ones would be 15. So take off 2 would be 13. That's among the options, at least. You will get some more practice for this one. And here are some examples how this is used in run length encoding. Remember, what we do in run length encoding is we store the first bit, starts with 0 or starts with 1. And then what follows is a sequence of these run lengths encoded using our new favorite toy, the Elias code. Very excited seagulls. Okay, let's go through some examples. We store a 1 because the first run here is with 1s, not 0s. How many 1s are this? 7-ish. So we need to store the number 7. Let's do this one more time. 7 is 111 in binary. So I prepend 2 zeros to signal that the length is 3. Okay? Now we have 2 zeros. That's in binary 1 0. Prepend the 0 for length 2. A 1 is mapped to a 1. We've seen that example before. These are 20 zeros. I believe my slides 20, I hope, is this in binary, 5 digits. So I prepend 4 zeros. Okay? Got the idea? One more for 11. 11 is this in binary, prepend 3 zeros, and there you go. Let's try to see, well, in this example, it worked quite well. Compressed it down to 63%. Let's do one more example of decoding. So first step, the first 0. Oh, is this pen? The first 0 says we start with a run of zeros. Then come 3 more zeros. So the length of the number we're reading is 4. So we take these 4. That was 13. So we produce 13 zeros in the output. Then we keep going. The next 2 numbers, we have 2 zeros. So we need the next 3 bits. That's 1, 0, 0, otherwise known as 4. So we append 4 ones. We read 0 zeros before the next one. So we read just 1 bit, and that is a 1. So we append 1, whatever the next thing is, zeros. There you go. And one last one, we read 1, 0. That means we read 2 more bits, 1, 0, which is known as 2. So append 2 ones. That's how run length encoding and decoding works. Okay. Now, if you don't have a binary alphabet, this alternation between zeros and ones no longer is enough. Instead, you have to say which is the next character. There's probably no way around this. And then you need to maybe come up with a smart way. How do you best encode that? Other than that, run length encoding also works for bigger alphabets. You can just write down a pair, now comes character A, so many times. And the so many times is again Elias gamma coded. And this is used in isolation. To be honest, run length encoding isn't that great, but it's used in some old formats at least. It is a quite simple algorithm, and so can also be implemented very quickly to run very quickly. And it's a part other than the Huffman code, which could essentially always just cut a text down to some smaller constants times n for a fixed alphabet. The run length encoding can be extremely effective if the input is extremely boring. And the ultimate case is if you have a file that's just n zeros, then run length encoding would find a single run and encode that using 2 log n bits. Right, log n for writing down n in binary and prepend as many zeros, -1. So that's a reduction from n to log n as a really strong compression. But of course, it only works in these very extreme cases if you have very few runs. More realistically, for most types of data in isolation, the compression is negligible. And so if you compare exactly how many bits you use, up to runs of length 6, you don't save anything. And for the specific numbers 2 and 6, the gamma code is longer than a run of that length. So you have expansion for some inputs, and you have compression for ones that have very long runs, more than 6. Remember, this was this no free lunch theorem that you will look at tomorrow in the tutorials, today or tomorrow. No? Maybe? So compression can't always work. You will always have, for each compression method, some inputs where it only makes things worse.